Welcome to Careless Coder. Today we will have a look at shader programming in Godot Game Engine. And we make it really stupid simple. If you cannot follow it along here, then you're probably stupid. Motherfucker! So shaders are a very powerful tool. And in the visual effects industry that I used to work in, we often use them as well. For example, for retro recipes where I made this one for them, the grid that is scrolling towards me indefinitely, that is just a shader on a plane. So shaders are really efficient because they run in parallel, they calculate the value of each pixel with thousands of little CPUs. And that's why they're so fast. But usually shaders are considered as very hard. The reason for that is, just like with assembly, because it requires a different way of thinking. You have only small building blocks, that is your basic arithmetic and your trigonometric functions. And those you have to combine to make something bigger. And I used to suck at maths. I'm really below average in maths. Applied mathematics sort of works with me, but not as quick as an average person. So if I can do it, you must even be better than me at it. And I used shaders a lot. So that was also something I played with Godot. When I got to explore Godot, oh, you can make shaders, cool. So I was playing around making little fractals, that sort of thing. Because that is really where shaders excel. So today we're going to make basically two shaders and we combine them in a single shader. That is a Pixelade Shader and a Chromatic Aberration Shader, because these are the two easiest to start with. The easiest to wrap your head around and, well, I think also easy to build up on. So let's jump in and have some shader fun. So we will first set up the scene. We make it very simple. We create a node 2D scene and we add a sprite to that. Where is it? Sprite, S-P-R-I-T. Yeah, typing is always difficult. There we go. And we add this little lovely photograph of this handsome devil. Right. At least there is no copyright infringement or portrait rights here. So in order to manipulate this image, we need to add a shader. So click on Materials, New Shader Material. Click on that material and we add a new shader. We call it Demo. Okay. So if we click on Demo, we have the source code here. Now the source code exists out of basically two components for a 3D shader and one component for a 2D shader. A 2D is a fragment and a fragment is the fragment of a color. And for 3D also have a vertex shader where you can move the vertices around. But since this is 2D, we will only use the fragment shader. So the first step in shaders is always to normalize that shader. So we're going to normalize it from 0 to 1 in the fragment shader. And the easiest way to do this is by using a little bit of mathematics. So we create a vector 2, a vec2, because a UV contains of a U and a V component, or X and a Y component. So vec2. And then we use the reserved word FRAGCOORD, and we take the XY position. Now these are the X and Y position of the pixel. And we actually, oh, I already revealed the whole code, sorry. FRAGCOORD, there we go, .xy. And we need to basically divide the X and Y with the resolution of the screen in order to get it into 0 and 1 space. So .x and Y component, and we divide it with the resolution. Now I had to look in the documentation because I could not find the actual resolution of the image. And then I found it, and in Godot it's a bit of a cumbersome way. You divide it over the inverse of screen pixel size. Now inverse of course is 1 over something. So 1 over pixel size. And the dot 0, these are all float numbers, hence the dot 0 or the dot. Usually I use just dot. Okay, so now it is normalized from 0 to 1 and from 0 to 1. And I can actually prove that now. Usually you want it in the center, but for now we're fine with this. But usually you want it from 0, 0 in the center, and then going up and going down. And I can prove this because if we use color, that's the reserved word, and we return the color for each pixel, and this is always a FRAG4. It has an R component, red, a green component, blue component, and an alpha component. So if we take the R and I put the uv.x in there and set the rest to 0 except for the alpha, because we want to see something actually, semicolon, and there you see it goes from 0 to 1. I need to stretch it a little because for some reason Godot doesn't show it there, but there you go, from 0 to 1. So we see that the X is normalized, and we can do the same with Y, of course. So let's change uv.x and uv.y, and we should see it going vertically from 0 to 1. Yeah, I already see something happening. Let's increase the size. And up there you see it will actually do that. So now we can read in the texture. We do that by using the texture keyword. We pass in the texture global, and that is the current texture. And then from where we want to read it, and that is our current UV. So if we now run this, we should actually see no change, except that we used a copy of the texture itself now. So let's analyze how a pixelized shader works. Well, we need to sample the color, and since we now have it in a color, we can actually do that. So we sample my iris, oh that's black, and then we draw an X amount of pixels black. Then we sample again, ooh that is brown, and we do X amount of pixels of brown. So basically it's a modulo. So let's capture my color in a color variable. So I just assign this to color, and let's do the modulo. So UV, we're going to change the UVs here, and we're going to add a modulo to it of UV and a very small value, something like this. You can convert this to pixels. We're currently not doing it, we're working in UV space. And we do it for the X and Y. So both at the same time, we set the same offset. Right, there is a typo here somewhere. What did I do? X and Y, that is correct. Modulo is correct. Oh, I'm missing the equal sign. There we go. So let's run this, because then we can see a bit better. And it doesn't work. Of course it doesn't, because the order of the color assignment and the UV is incorrect. So we need to move the color down after we manipulate the UV. So let's move this over. And yeah, the order of operations is very important in shaders. Okay, and now I already see some pixelation happening, and we run it. And yeah, there is some pixelation. YouTube compression maybe reduces it, but it's also not correct in the right order. Because we update the UV, we're basically folding the UV over itself, so it looks a bit fuzzy. It isn't really correct. So we need to offset it down as well by multiplying it by -1. And this is how you do shaders. You make little incremental changes. And that way you can follow along. And that's the same way how we also program assembly. You don't take the whole big problem at once. Okay, that already looks better. I can see that in the little preview, but let's run it. And there you go. I think a lower resolution is an improvement for my face, don't you think? Now you can also make functions. In this case it's a bit useless, but yeah. Let's put this in a function. We need to pass in all the parameters. So we first need to find out what this was. Texture, but that's a sampler 2D. We call it T. And then we need our UVs, of course, which is a vec2. And then the vector, how much we want to pixelate. We copy everything in, we return the color. And here pixelate, and we just call it like this, and it's the same. So now you also know how to use functions to organize your functions, your mathematical functions. Okay, let's do the aberration.
In order to model it, we first need to understand it. So what is chromatic aberration? Well, a lens is not equally wide, and the wavelengths of the red, green and blue are not the same wavelength, obviously, otherwise they wouldn't have different colors. So the blue travels a bit faster through the glass than the red, and that is really noticeable at the edges of a lens. So red lines up to the left and blue lines up to the right. And that is why cinema lenses are very expensive. They reduce it to a visible minimal. So let's offset the red to the left and the right to the blue. That should work. So what we need to do is we need to sample the same texture again and then an offset on X with a little bit for only the red channel and the same for only the blue channel, but there we will offset it positive. So now when we assign those colors, we should have chromatic aberration. And there we go. Red to the left and blue to the right. But there is a little problem. The aberration is all over the picture and usually it's only in the corners where we see the chromatic aberration. So we're going to use mask. We're going to put a mask over my face, basically enhancing it by masking it off, and only apply the aberration on where the mask isn't. So let's create the elliptical mask here, and let's also do a comment over here. It's very important to comment your shaders because mathematics isn't really that easy readable. Alright, now how do we make an ellipse? Well, basically we take the distance from the center here. So if we take the center and we move further away, the color gets darker, and closer it gets whiter. Now how can we do this? Well, there is this magical thing called a smoothstep, which interpolates between two values based on an actual value. So we want to oscillate between 1.0 and 0, or well, close to 0, 0.1 in this case, but you can make it 0, and based on the UV distance, because we want the UV. However, this will not completely work in our case, because remember, the UV starts from 0. So let's visualize our mask by assigning it to the color, disabling the color beneath, so we can see how it behaves. Well, the way that we expected, from 1 to 0. That's not what we want. So let's see what happens if we use the dot product to actually move it over. Now, a dot product is when you have two vectors, and when they're perpendicular, the value is 1, and when they're parallel, the value is 0. So yeah, that should at least get us in the ballpark. So let's visualize this and see how close we are. So we're basically sneaking up on the solution, and this is why applied mathematics works for me and theoretical doesn't. So we just need to offset this. We need to multiply it by 2 and then subtract 1, and I think we will dare. So let's introduce a nice variable which actually holds that little piece of math that we're going to implement here. So we create a trans variable and we multiply the UV by 2. So then we're shifting it all the way up, but then we overshoot and then we just subtract 1. And let's see. Something went difficultly wrong here. Technical difficulties. Trans. Oh, yeah, it needs to be a vec. And let's run this. Yeah, so actually multiplying works, and now we need to subtract from it the 1.0. And this is how you should approach these problems. That will make shader languages easy. People want to immediately create this effect. No, you need to sneak up on it. And yeah, since it's an ellipse, it's really easy. We don't need to make it center like a circle. So this should work. We now need to mix it. That's it. So now we're going to mix the ABR with the original image. So not assign it to the whole image like we did here, but we're going to assign the red, and we're going to mix the AB red with the original color image texture. So ABR, comma, and then color, comma, and then our mask. Oh yeah, and we need to do it only for the R channel, of course, the red channel. Right, mask with a lowercase. Oh, my caps lock is stuck again. There we go. And we also need to do this for the B channel. And basically what it does is when the mask is white, we will use the original color, and when it's black, we use the aberrated color. And I see a typo. This should be ABB instead of ABR. Yeah, it's purple, alright, so let's fix that. But you can also see that it's in the center, it's perfectly normal. Well, as far as my face can be perfectly normal. It's funny that when you're narrating your coding, you see these bugs, and when you code them, you don't. So yeah, that should now work. Yeah, we got a nice blue and red fringe on the edges, and I'm pixelated as hell. I would say this is a massive improvement. But we can improve it even better. We can actually animate the aberration. Although in real life that wouldn't happen, but who gives a fuck? This is art. So we change that offset, fixed offset with a sign of the times, great album by Prince, and we multiply it so we can scale it down to that same range, because a sign over x always lies between -1 and 1, if you remember your high school trigonometry. And we do the same for the B channel, of course, but there we do the offset, and yes, it will cross over to left and right, which in chromatic aberration isn't correct, but this is art. And we like to see that. So yeah, so now we should have moving chromatic aberrations. Let's check this out. So yeah, it's moving, albeit a little slow, but it is moving left and right. This looks really cool. And we can speed this up by multiplying the time value. And we all know that faster is always better.
So there you have it, a 2D fragment shader, really simple. That already does quite a lot of interesting things that you can even use in your game. So yeah, and then build upon this. And if anything, this is where learning trigonometry is actually getting fun, because you can apply it, unlike what we had to do in the 80s in a classroom with graphing paper, like, ugh, fuck that shit. But here you actually see your results instantly. So that's really cool. So I hope you learned something, and we probably will revisit every now and then a couple of more shaders. Maybe I will do that scrolling raster shader from retro recipes that I made for them. So yeah, I hope you learned something, and see you in the next one.